So in the last video we defined the spherical transformation, so the spherical coordinates in three-dimensional space. We said that given a point P here in three-dimensional rectangular coordinates x, y, z, this point can be thought of as lying on a sphere of radius rho. So the radius of this sphere is rho, sphere of radius rho, with a couple of different angles prescribed. So the first angle, opening this way, we called phi, and then the second angle, which opened in the usual way of polar coordinates down here on the xy plane, this angle was called theta, and together these three pieces of information uniquely describe the point P. And remember, this symbol right here is a rho, so the point's called P. The rho is like a curly looking Greek letter, but this is rho, phi, theta. And so it's going to be important for us to understand how, or at least to set some conventions as to how we are going to trace out or fill out solids in space in these spherical coordinates. And so here are the conventions that we are going to set together for our class for spherical coordinates. And the reason for doing this is that we are going to at some point have to figure out how to integrate over three-dimensional regions using spherical coordinates. And of course that's going to require us to compute the Jacobian and the volume element dv in this space. And we'll do that in the next lecture. But in this lecture we just want to, like I said, set some conventions. So spherical coordinates are like the three-dimensional analog of polar coordinates in the plane. And of course that means that there's a special point, which is the origin in rectangular coordinates, but this point is called the pole in both polar coordinates and spherical coordinates, or we can still call it the origin if we want. We'll call it O. And this point O is the one point in space that is uniquely described by less than three pieces of information. So the only piece of information that we need to describe this point O, this pole, is that the radius, the rho, is equal to 0 at this point. Okay, and this is the only point in space for which this is true. Every other point in space has a positive radius, so rho is positive for all other points. Again, we're setting convention here. Just like in polar coordinates, the radius can be thought to be negative in certain situations, but it changes the geometry of your, at least the way that you think of the geometry of your region. So we're going to say that rho is positive, and I drew rho in orange over here. So as rho changes, rho is going to vary in a way that it's going to increase as we move out the positive z-axis. Okay, so positive rho is going to start at the pole and move out the positive z-axis. All right, so there's our convention for rho. Once we have traced out this length rho, this puts us on a circle now. So this determines a sphere of radius rho. So this determines the radius of the sphere for which our point lies on that we're concerned about. And from this point, now we're kind of at the north pole of our sphere. Now we need to rotate around and get to the point that we care about. And so our convention then, we've discussed this a little bit, our convention then is that the angle phi now takes this ray that's been traced out and it rotates it toward the positive x-axis. So from the positive z-axis toward the positive x-axis, this is the angle phi. And so if we think of it as tracing out, this is now in your mind coming out of your screen, this angle, in the direction of the positive x-axis. So I'll draw the positive x-axis here for us just to use for comparison's sake. And this angle is being traced out this way. And now we have to make some other choices here. So this angle phi, its positive direction is from the positive z-axis toward the positive x-axis. And we need to kind of set a range for this. So as phi varies from 0 to pi over 2, we trace out this upper half here of the circle. And then it can continue to vary all the way until it gets, it could go all the way around. This is supposed to be coming out of the screen, remember, so this is an entire semicircle at this point. And at this point, straight down here, this is the angle pi. so this is phi equal to pi, this will trace out an entire, what you might think of as like a fan or a semicircle, semi-disk, half of a disk, in the direction that comes straight out of your screen. And remember, it traces it out by just taking these rays from the pole to the angle, and it just fills this out. So our convention is going to be that our angle phi is allowed to vary from 0 to pi, but that's it. Okay, and again, this is a choice that we're making. There's nothing stopping us from allowing this angle phi to continue back through to the back side of our screen and continue on the back side here. But we're going to set this convention that our phi varies from 0 to pi. So, and our convention for rho is that it's non-negative and it's only equal to 0 at the pole. Every other point has a positive radius rho. Okay? And now we want to fill out the rest of the sphere at this point. And so the reason for choosing this restriction on phi is that we want the angle theta to behave exactly the same way that we're used to theta behaving for cylindrical and polar coordinates. What I mean is that theta opens from the positive x direction toward the positive y direction, and it's allowed to vary all the way around the circle and go from 0 all the way back around to 2 pi. Okay, so this angle theta now takes this entire fan, which is coming out of the screen, and it rotates this all the way around from 0, the angle theta equals 0, back to the angle theta equals 2 pi. Okay, and as it does this, the green fan is going to go with it, right, the entire way. And my drawing is very poor, but this is supposed to be tracing out, it's filling out an entire sphere at this point. So use your imagination, because this sphere looks pretty jammed up, especially right over here. But the idea is that we first travel out to the radius, so the radius varies from 0 out to whatever value your radius is at your given point. Then that ray is rotated out of the screen toward the positive x direction, creates a fan type shape, and then that fan is rotated around the z-axis, by this angle theta. And so our final restriction then is that theta, or our convention, is that theta varies from 0 to 2 pi. And so we are going to stick with these, we're going to stick with these conventions for sure, and we're going to stick with the order of operations here, that we go out rho first, then we rotate down by the angle phi, and then we rotate around by the angle theta, in that order, so that the coordinates of our point are truly exactly this: rho, then phi, then theta. Okay, the order is going to matter for us. Again, it's a convention that we're setting, but we want to all be on the same page. So this is the convention that we're all going to use when talking about our spherical coordinates.